Hi, we're Group 21, Seneth and Justin, and today we are going over the design and analysis of a walkable robot using 4-bar linkages for EGB321. For this task, the mechanism constraints are that the motor shaft continuously rotates 360 degrees, implying that a Grashof crank rocker-rocker type mechanism is desired. The Grashof condition of shortest plus longest being less than or equal to the sum of the other two linkages must be followed. Additionally, the transmission angle mu must be in the range of 40 to 90 degrees for smooth travel. And finally, the geometric constraints must be considered to avoid collisions with other linkages. The process for the linkage size selection is as follows. First, constraint definitions, which are the basis for the linkage parameter ranges. Next, kinematic filtering using a MacLeod sweep was performed to remove invalid linkage combinations, with the criteria of the Grashof condition and the transmission angle used as mentioned previously. After that, weighted scoring is done on valid designs to rank the top 5, as seen in Figure 1, based on equally weighted metrics for horizontal step distance and foot trajectory flatness. From this, the top 5 ranked were compared, and it was found that rank 3, which is a purple trajectory, had the best balance of ground contact, center of mass, and clearance. Finally, the rear linkage was synchronized, where the rear coupler was selected to ensure a similar ride height to the front. Keep in mind that at a given time, the front left foot and rear right foot would be touching the ground and vice versa. Therefore, the finalized design parameters are obtained, which also satisfy the Grashof condition and transmission angle range. With reference to Figure 2, the results for each linkage can be seen in the table below. It should be noted that the crank is shared between front and rear linkages. Next, the kinematic analysis results are as shown below. For the open configuration system, the position, velocity, and acceleration analysis were calculated based on crank angle θ2 being 60 degrees, ω2 being 12.56 radians per second, and α2 being 0 radians per second squared. Continuing on, the front and rear angular velocities for links 3 and 4 versus the crank angle θ2 is shown, where it can be seen that there are smooth curves only, indicating no sudden accelerations, prolonging the lifespan of the mechanism. For fabrication, rapid prototyping was used with an FDM 3D printer, the QUT EGB321 Pro, using PLA filament for a lightweight, rigid chassis and linkages. The joining method used was M3 screws with nylon insert lock nuts to ensure low friction during linkage rotation and to prevent loosening due to vibration, as seen in Figure 4. To address floor traction, TPU 95A was used to create feet that elastically deform and maximize surface contact, effectively minimizing slip, as seen in Figure 5.